So in this one we can either proceed with trying to find all the number of invertible matrices, trying to calculate the number of invertible matrices, but that would lead to a lot of cases. So the easier approach is to find the number of matrices which are not invertible, because there are lesser cases for that. So first let's see what the determinant value is. So it's A3B C2D, and I'll find the determinant value with this row. Because we have two zeros here, determinant value will simply be 5, this into this minus this into about minus 5 times. If I want this to be invertible, I just want that AD should not be equals to BC, or rather I want to find the matrices which are invertible, so AD equals to BC. So now I make cases. Case 1 was to 0. So I have to let's say I keep A 0, then I can have 7 non-zero values for D, so there are 7 ways. Similarly I can make A D 0 and A non-zero, so there are 7 more ways, plus both are 0, both A and D are 0. So these are all the possible combinations of digits from our set which I can put as A and D, so that the product AD is 0. So this is 15, so there are 15 different ways for this, and similarly there would be 15 different ways for this because there's no difference. So the total ways for AD equals to BC equals to 0 is 225 different arrangements. Now the next case would be AD equals to BC, but they are not 0. So again, now as they both are not 0, I cannot keep 0 in any of these 4 places. So my set of elements which I need to place here is of size 7. So these are 3, 5, 7, 11, 13, 17 and 19. Also notice that all of these are prime numbers. So if I keep 2 numbers here, the same 2 numbers should appear here. They can be in different order obviously. So let's say I keep any of these 7 numbers here, so I have 7 choices, and then I can keep the same number here, so that's 1. So in that case the same 7 the same 2 digits, the same digit should be at both the places. So yeah, so the total number of ways to place the same digit in the 4 places is 7. If there are 2 different digits here in these 2 places and consequently in these 2 places, the number of ways would be 7 into 6, and for each of the pairs we keep here, there will be 2 arrangements for this, so this into this into this. So what I counted is by 7 is the total of these 7. I can keep any one digit here. 6, as I want to count the number of ways in which I put 2 distinct digits here, so if I keep 5 here, then I will be able to keep the remaining 6 digits here only. That's why into 6. And say I keep 5 and 7 here, which are included in these cases, then I'll be able to keep 5 7 or 7 5 here, so that's why 2. So this becomes 7 into 13. So case 2, there are 91 distinct arrangements. So the total cases, total arrangements for making this matrix determinant 0 is 316. The total matrices simply would be a to the power of 4, because each of the 4 A, B, C, D positions can be filled by any of these 8 digits, which is 64, or rather 2 to the power of 12, which is 4096. So the answer is 4096 minus 316, which is 3780. So the answer is 3780.